Hi, in this video, we present our 64212 robotics manipulation project, dexterous in-hand reorientation using reinforcement learning. My name is Pierre, and I will be joined by my teammates Martin and Alessandro to share our work with you. Complex robotics tasks are becoming more and more feasible with advancements in computational control methods. Incredibly complex motions, such as dexterous manipulation, are difficult to parameterize and express compactly. Additionally, highly intricate plants with as many as 20 or more degrees of freedom require stable and accurate commands for each of their individual actuators. One important class of abilities for the modern robot is dexterous manipulation of objects, familiar or foreign. For robots to perform well and to be useful, we can imagine several situations in which they must physically manipulate objects, such as picking fruit from a tree, handling kitchen tools, drawing and erasing whiteboards,
Wow, that's impressive.
and playing sports and more. That premise motivates a better programming method. In our project, we explore one solution, reinforcement learning, an optimal control technique which generally involves the interaction of agents with an environment conditioned by a reward function. Control policies are initialized and trained over several iterations, ranging from hundreds to several orders of magnitude, and the parameters of the systems are updated based on user-designed rewards. The goal of our project is to develop reinforcement learning-based policies for a robotic hand to manipulate the orientation of a basic object in simulation. We set out to train a mechanically intricate hand with a reasonably high number of degrees of freedom to accomplish this task reliably and quickly.
Thanks for that introduction, PA. I'm Alessandro, and before even the first RL model can be trained, we reviewed a number of related works to understand what current research can accomplish and better inform our iteration process. Here's a list to name a few: Declaw, Shadow, Allegro, and Leap. After careful consideration, we decided to train the Leap Hand, a project out of Carnegie Mellon University designed to be a low-cost alternative to expensive market standards, yet versatile enough to be a suitable hardware for robotic learning. Leap has published several examples of its dexterity capabilities, but we also believed that we could extend the limitations of the available work with our own training methods. Leap is a 16 degree of freedom, 4-finger, open-source mechanical hand. For simulating the Leap hand, we relied on NVIDIA's Isaac Lab and the physics GPU-accelerated physics, which support rich manipulation dynamics and realistic modeling for both friction and compliance. We created an environment to batch many parallel simulations for massively increased RL throughput. In training, we implemented customized curricula and iteratively improved reward functions. We also improved the deployment of the inference model in order to test custom control inputs.
Hi, this is Martin. Let's see how we implemented these policies. Our goal was not just to spin the cube, but to accurately reach a commanded angle, pause there, and wait for a new command. The original example code from the Leap team was not goal conditioned and would just spin forever. As a preliminary iteration, version 0 successfully oriented the cube to a goal angle, but we did it through the environment by pausing the pre-trained policy, not actual goal conditioning. As a result, it would only spin counterclockwise. For version 1, we trained our own policy with proper goal conditioning and knowledge of the cube's orientation. We introduced random sampling of target angles during training using quaternions as a compact, singularity-free representation. Additionally, we incorporated torque, velocity, and fingertip distance penalties, and we reset the episode and gave penalties when the cube fell or flipped. The policy spun in both directions, but it worked quite slowly and only worked well for small angles. For the second version, we introduced evenly spaced intermediate reward checkpoints and penalties that encouraged stable holding. Speed and steady state error improved, but its success rate and consecutive goal successes went down. For version 3, we only apply the angular velocity penalty near the goal and remove a default pose penalty to prevent conflicting rewards. We also gave increasingly large rewards for each consecutive success to encourage reliability. This was a big improvement in success rate and consecutive successes, but at the cost of speed, likely because it learned to be more cautious. We were saturating the performance possible without translational information. For our final one-dimensional policy, version 4, we conditioned on the cube's full global pose, not just orientation. Additionally, the fingertip distance penalty was removed, so fingers couldn't hamper the cube's mobility. We also capped success reward within a region of the goal angle for stability. This fourth and final policy was extremely fast, had a near-perfect success rate, would stop right at the goal, and keep the cube stable in its palm. Finally, we extended to full 3D reorientation by directly sampling a quaternion in SO3, with angle error now based on the geodesic distance. Now, the policy can rotate the cube in any direction in space. Here are some plots summarizing our results. We see our fourth iteration of our 1D policy dominate most metrics, while versions 1 through 3 chronicle our journeys in finding trade-offs to multiple approaches, combining the best of them to make version 4.
Several attempts at this problem of arbitrary 3D orientation have been made throughout the research sphere. we are proud to say that the models we trained and the performance improvements we measured were due to our ability to shape the reward function and training process more efficiently.
First, we achieved monodirectional control, then bidirectional control, and finally a first pass at full 3D reorientation. Nevertheless, there are still several improvements to be made and potential iterations to continue this work. We did notice during testing, however, our best 1D policy would still take an inefficient path between the plus and minus 180-degree discontinuity due to the checkpoint system, which is a straightforward fix but would require retraining. Robust 3D reorientation also needs more work. The current error metric, geodesic quaternion distance, may not be optimal. The policy does often reach the goal pose, but sometimes doesn't make progress at all. Alternative trajectory planning methods could be computationally intense, but more efficient for training and deployment. We hope you enjoyed this exploration of the reinforcement learning process. Just like the leap hand, we learned a lot too. Thank you for watching.